Imagine sitting down to work at a small desk. In a computer, this desk is the cache, a temporary workspace with strictly limited room. Keeping your tools right in front of you means you can grab them instantly. If you had to walk across the room to a massive bookshelf every time you needed a pen, your work would grind to a halt. That bookshelf is like your computer's main hard drive. It holds everything you own, but getting to it is incredibly slow. But as your daily project grows, your coffee cup, calculator, and sticky notes start fighting for real estate. Soon, the desk is completely covered. Your computer's cache hits this exact same wall when it reaches its maximum capacity. Now, a massive new textbook arrives that you absolutely need to open right now. But there is physically zero space left on the desk to put it down. To keep working, you have to make a tough choice. You have to pick one item to banish back to the slow bookshelf. Computer scientists call this harsh decision-making process an eviction policy. So look at the mess in front of you. Which specific item is the least worth keeping on the desk to maintain your efficiency? You wouldn't pack away the pen you literally just set down, and you certainly wouldn't toss the notebook you are currently writing in. The most logical target is that dense formula sheet sitting in the corner. You needed it a few hours ago, but you haven't glanced at it since. That natural human intuition, removing the thing you haven't touched in the longest amount of time, is exactly how computers solve their own memory traffic jams. This everyday logic for cleaning off a workspace is actually one of the most widely used computer algorithms in the world, LRU. LRU stands for least recently used. When a system runs out of room, it kicks out the item that has gone the longest without being accessed. It completely ignores the physical size of the item, its business importance, or its original creation date. The algorithm has only one operational metric. It simply measures which item has sat untouched the longest. There is a common trap here. It is very easy to confuse how recently an item was used with how frequently it is used. Let's bring two contrasting items to the desk to see the difference. First, you have a stapler. You used it 200 times yesterday to bind a massive report. That is high frequency, but you haven't touched it at all today. That means it has very low recency. Contrast that stapler with a pink highlighter. You have only used it twice in its life, but the last time you uncapped it was just 30 seconds ago. The LRU algorithm strictly follows recency. It ignores the stapler's high lifetime tally and evicts it, choosing to protect the recently touched highlighter instead. In the LRU mental model, a single recent touch is far more valuable than a mountain of past stale usage. Now let's translate that physical desk directly into a digital scenario. Imagine your workspace is the cache for a multiplayer video game server. The active data includes live leaderboards, active player profiles, and current inventory states. Suddenly, a massive influx of new players logs in for a weekend event, instantly filling the server's limited cache to 100% capacity. To keep the game running, the server deploys the LRU rule. It scans all the active data to find the one player profile that hasn't made a move in 2 minutes, and it swiftly deletes it. By evicting the inactive player's data, the game server stays lightning fast for the players who are currently actively mashing buttons. This underlying behavioral assumption is exactly what makes LRU an industry standard. It perfectly maps to the concept of hot versus cold data. Hot data is information we are actively touching. Human behavior consistently shows that if you just looked at a file, you will almost certainly need to look at it again in the next few seconds. Cold data represents the items gathering dust. Because they haven't been used recently, it is a very safe statistical bet that they won't be needed immediately. LRU works because it naturally protects that hot data. Prioritizing active information directly improves the system's speed and reliability. This exact principle is what keeps our favorite global entertainment platforms running without lag. Take a look at this PlayStation console. Gaming hardware relies heavily on strict cache rules to manage its limited physical memory, ensuring the textures and assets for your current level load seamlessly. Or consider this massive stack of Netflix envelopes. Today, Netflix streams video digitally, but they still use cache management to quickly deliver the exact movie you were just watching, rather than searching their entire global database every time you hit play. Even social media apps like TikTok use similar background memory rules. They rely on short-term cache to manage your endless video feed, ensuring your phone doesn't crash when you switch between scrolling and texting. So the next time your devices run perfectly smoothly under heavy use, you can thank the invisible LRU rule, constantly cleaning off the digital desk behind the scenes.